Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so the first question gives two different Ka and Kb values. So the Ka of ammonium plus is 5.6 times 10 to the negative 10, and the Kb of a cyanide ion is 2 times 10 to the negative 5. What would be the resulting pH of a salt solution? Okay, so for this question, they give us the Ka and the Kb values, and we just need to know whether or not the resulting pH would be acidic, basic, or neutral. So I'll show the reaction of an ammonium plus and Cn minus. And we pretty much just need to compare the Ka and the Kb values. So the Ka is 5.6 times 10 to the negative 10. And the Kb is 2 times 10 to the negative 5. So if we look at our two values, then we notice that Ka is smaller than Kb. So therefore, the resulting pH would be basic. Okay, so now let's see what the junior tutor said. The resulting pH of a salt solution follows the rules below. If Ka is equal to Kb, then the resulting salt solution is neutral. If Ka is greater than Kb, the resulting salt solution is acidic. And if Ka is less than Kb, then the resulting salt solution is basic. Therefore, the resulting salt solution of ammonium cyanide would be basic. Yep, so this solution is correct. Okay, so question 2 is just a balancing of the reaction. We have hydrochloric acid plus barium hydroxide produces barium chloride plus H2O. Okay, so let's look at the barium first. So you'll see there's one barium on both sides, so that's good. Next, we'll look at the chlorines. I'm just going to say balance. Chlorine. You'll see that there are 2 atoms of chlorine in our product side and only 1 atom of chlorine on our reactant side. So I'm just going to put a coefficient of 2 in front of HCl, sorry. And after we put the coefficient in front of HCl, you'll notice that I now have more hydrogens on my reactant side. So the second step is just to balance out my hydrogens. So since we have 4 on this side, I'm going to put a coefficient of 2 in front of water. Now let's double check to see if everything is balanced. 2 oxygens, 1 barium, 2 chlorines, and 4 hydrogens on both sides. Okay, so let's see what the junior tutor said. A balanced equation has the same number of atoms of each element in the reactant and product side. In the given chemical reaction, the following are the number of atoms for each element in the reactant and product side. So they wrote down how many of each element there were on each side. So there were 3 hydrogens, 1 chlorine, 1 barium, 2 oxygens, and then 2 hydrogens, 2 chlorines, 1 barium, 1 oxygen. Starting off with chlorine, a coefficient of 2 can be added to HCl. And then they updated column. And then a coefficient of 2 can be added to H2O to balance the number of hydrogens and oxygen. Okay. So they ended up having the same balanced equation. So this solution is correct. Okay, so question 3. What is the balanced chemical equation for liquid methanol combusted in oxygen gas to yield carbon dioxide gas and liquid water? So this is an example of a combustion reaction. And first, let's write down all of our reactants and products and the state that they're in. So we have methanol, which is a liquid. It was combusted in oxygen gas, so O2 gas. And then my reaction arrow, and this takes place under heat. So I'll put that little triangle top of the reaction arrow. And our products are CO2 gas and H2O liquid. Okay, so normally when I balance combustion reactions, I like to balance out my carbons first, since there's usually multiple carbons in the reactant side. But in the case of methanol, there's still only 1 carbon, so I'm going to skip balancing the carbons. And I'm just going to balance out my hydrogens next. So you'll see there are 4 hydrogens on our reactant side and only 2 on our product side. So step 1, balance out the hydrogens. So there's 4, so I need to add a coefficient of 2 in front of water. And now you'll see that this affected the number of oxygens as well. So now we have 4 oxygens on our reactant side, but we have an odd number of oxygens on our we have an even number of oxygens on our product side and an odd number of oxygens on our reactant side. So in times like this, I would need to add a coefficient of 3/2 in front of my O2 in order to also get 4 oxygens on both sides. So you'll notice that since I only had 3 on this side, I wanted to add a coefficient in front of my O2, just however many remaining oxygens I needed, and then divided by 2, just so that it will cancel out that O2. Okay, so step 2 was to balance out the oxygens. And now notice that my coefficient contains a fraction. So I'm going to multiply by 2 to get rid of the fraction. So when we multiply, we want to do this to the whole reaction. And then our new balanced equation is 2 methanol plus 3 oxygens makes 2 CO2 gas plus 4 H2O liquid. Okay, so let's see what the junior tutor said. To balance a chemical reaction, we can use the method of inspection. And this method, we multiply the species that we are to balance by a coefficient. First, balance the elements that are not oxygen and hydrogen. Then we balance whichever is simpler. To start, we translate the reaction into a chemical equation. So since carbon appears to be balanced already, we proceed by balancing hydrogens. We balance hydrogen before oxygen since hydrogen only appears in 2 species. The result is shown below. Okay, so they put the 2 in front of H2O. Next, we balance the oxygen. The easiest way to do this is to multiply 2 to the methanol. Okay, so they put their 2 in front of methanol first. Then they say that this makes carbon and hydrogen imbalanced, so we need to adjust accordingly. So then they just switched their coefficient of 2 to a coefficient of 4, and then put a 2 in front of carbon dioxide. Now we need to balance oxygen for the final time. The balanced chemical equation for the combustion of liquid methanol and oxygen is shown in equation 1. Yep, so they ended up with the same balanced equation. So there are 2 different ways you can go about answering this question. It just depends on whether or not you like to deal with the fractions, or if you don't mind going back a few steps to fix your coefficients. Okay, so this solution is correct. Okay, so question 4 is just kind of like a fill in the blank. Most organic compounds contain carbon and blank. So even just kind of browsing through the options, we know that the answer to this is hydrogen. Because you'll notice that with most of organic compounds, like if we had ethane, since carbon prefers to have 4 bonds, when it isn't bonded to another carbon, it's most likely bonded to more hydrogens. Even when we have double bonds involved and triple bonds, we namely have carbon and hydrogen bonds in the sample. Even like with benzene rings, which has a double bond in between every other carbon, all of them contain a single bond to hydrogen. Okay, so these are just some examples of some organic compounds. And the junior tutor said that the answer is letter D. While some organic compounds may contain nitrogen, oxygen, sulfur, and even phosphate groups, many organic compounds are formed from chains of covalently linked carbon atoms with hydrogen atoms attached to the chain, a hydrocarbon backbone. Organic compounds are molecules that contain carbon atoms covalently bonded to hydrogen atoms. This means that all organic compounds have in common the presence of carbon atoms and hydrogen atoms. Yep, so this solution is correct. Okay, so question 5 is to determine the oxidation number and oxidation state, which is the same thing, of each element in the following 6 compounds. And then they give 6 different compounds. So first I'm just going to scroll down a bit and look at the rules that the junior tutor has written down. So when we determine the oxidation number of an atom in a compound, we usually follow these guidelines. Number 1, atoms have an oxidation number of 0 in their elemental state. 2, monatomic ions have an oxidation number equal to their charge. And then 3, in compounds, carbon is usually assigned an oxidation number of +4, but it can be 0 as well. Chlorine is usually assigned oxidation number of -1. Oxygen is usually assigned an oxidation number of -2, except when it is part of a peroxide, it would be -1. And in binary compounds with fluorine, where it is positive. And hydrogen is usually assigned an oxidation number of +1, except when it occurs as the hydride ion, under which case rule 2 wins. So in compounds, an oxidation number is given to all other atoms such that the sum of the numbers of oxidation on all atoms in the sample is equal to the charge on the molecule. Okay, so now let's put the rules into work. We have copper carbonate up first. So recall that oxygens typically have an oxidation number of -2. But since there are 3, then its total contribution of charge is -6. So I'm going to show just the contribution of all the oxygen atoms, but I'm going to circle -2, since when we report the oxidation number, we report it for a single atom. So the oxygen's oxidation number is -2. And then in the case of the carbon, one of the rules said it typically has an oxidation number of +4. So I'm just going to write that in, since it is likely to be +4. And now notice that we know carbon's oxidation number is +4 and oxygen's was -2 times 3. So if we added these charges together, we have -2. So if you see that the compound is neutral, then we need to neutralize the -2 that the carbons and the oxygens have taken place. So in the case of copper, it would have an oxidation number of +2 just to neutralize all the other oxidation numbers. Okay, so this is the answer for 5A. Now let's look at B. We just have methane. So in the case of typically, yeah, I was wondering about this. So the carbon typically has an oxidation number of +4. But in the case of the hydrogens, hydrogen usually has an oxidation number of +1, like what they mentioned in the rules. But in order to neutralize the +4 from carbon's oxidation number, it makes sense if the hydrogen has an oxidation number of -1. And since there are 4 hydrogen atoms, then this balances out the carbon. Okay, so on to C. We have iodine and fluorine bonded together. So fluorine usually has an oxidation number of -1. So the iodine will have +1. Okay, so now let's look at D. We have CH2Cl2. So in the case of chlorine, its oxidation number is -1. So I'm going to circle that in green. But again, since there are 2 chlorine atoms, I'm going to multiply this by 2 just to show the overall charge is -2. In the case of hydrogen, typically has an oxidation number of +1. But again, there are 2 hydrogen atoms, so I'm going to multiply this by 2, and you get +2. So now you'll see that the hydrogens and the chlorines cancel each other out. So that means the oxidation number of our carbon would just be 0. Okay, on to E. We have sulfur dioxide. So again, oxygen typically has an oxidation number of -2. I'm going to circle that. There are 2 atoms of oxygen. So overall, it gives off a -4 charge. And to balance this out, 1 sulfur atom should be +4. And then lastly, we have Nh4 Ammonium Chromate. Okay, so this example is a little more tricky, but it's easier if we were to separate them into their ions. In the case of Nh4, this is the same thing as writing its single ion. And then let's do the same thing for the chromate. Which has a charge of 2-. Okay, so let's do the ammonium first. So if we recall that hydrogen tends to have a +1 oxidation number, since there are 4 atoms, then overall they give off a +4 charge. So I'm going to circle +1 since this is the answer for the hydrogen. And since the ammonium ion has an overall +1 charge, that means the oxidation number for nitrogen should only be -3. So this gives us an overall +1 charge for the Nh4 ion. Okay, so now let's do the same thing for the chromate. Oxygen typically has an oxidation number of -2. So I'm going to circle that in green. But there are 4 oxygen atoms. So let's multiply this by 4. And it gives off an overall -8 charge. So if we want our chromate ion to have an overall -2 charge, then that means that the chromium should have an oxidation state of +6. Okay, so now let's see what the junior tutor said. In determining the oxidation number of an atom in a compound, we usually follow these guidelines. Number 1, atoms have an oxidation number of 0 in their elemental state. 2, monoatomic ions have an oxidation number equal to their charge. 3, in compounds, carbon is usually assigned an oxidation number of +4, but it can be 0 as well. Fluorine is assigned an oxidation of... Oh yeah, I read this part already. But yeah, this is just a reminder. So again, there are some instances where some of the compounds might have exceptions. So that's why it can get a little bit tricky, but you kind of get the hang of it the more you practice finding oxidation numbers. So here's what the answers say for letter A, copper carbonate. Overall charge is 0, so they have oxygen having a -2 oxidation number. Carbon is +4, copper was +2. CH4 was kind of confusing to me as well, since hydrogens usually have a +1, but I just said that if carbon had a +4 oxidation state, then the hydrogen should be -1 if the overall molecule is neutral. So I'll just take note of that at the end there. -1 for fluorine, iodine +1, hydrogen +1, fluorine -1, carbon in this case would be 0. Oxygen is -2, sulfur's +4. And then they separated the last compound into their individual ions and got +1 for hydrogen, -3 for nitrogen, -8 for oxygen, and then +6 for chromium. Yep, so this solution is correct. Okay, so I just added my bit. Okay, so now we're on to question number 6. Find the number of ibuprofen molecules in a tablet containing 200 milligrams of ibuprofen. Okay, so this is a multi-step question. First, let's write out what we are given. We're given the mass of ibuprofen, which is 200.0 milligrams. But I will convert it to grams just to make it easier for my calculations in the future. I'm just going to write 0.2 grams. And then they give us the chemical formula for ibuprofen, C13H18O2. And we want to find the number of ibuprofen molecules. But the first step is to just find the molar mass of ibuprofen. So molar mass can be denoted as a capital M of C13H18O2. So to find the molar mass of this overall compound, we need to first determine all of the atomic masses of the individual atoms. So these are just values you would find on your periodic table. And we want to multiply by however many atoms are in the compound. So in the case of carbon, there are 13 carbon atoms. So we're going to multiply 13 by the molar mass of carbon plus 18 times the molar mass of hydrogen plus 2 times the molar mass of oxygen. Okay, so on the periodic table, you'll find that for carbon, it has an atomic mass of 12.01 grams per mole. For hydrogen, it is 1.01 grams per mole. And for oxygen, it is around 16 grams per mole. Okay, so if we multiply it all out, we should end up getting a molar mass of 206.31 grams per mole. Okay, so that's part 1 of answering the question. Second part is to now find the number of moles of ibuprofen. So to do this, it is just the mass divided by the molar mass. So this is why I converted our 200 milligrams to 0.2 grams, just so that it is, I can cancel out the grams when I divide by the molar mass. So it's going to be 0.2 grams divided by 206.31 grams per mole. The grams will cancel out, and our number of moles is 9.69 times 10 to the negative 4. Okay, so lastly, we can answer the question. Find ibuprofen molecules. So now we want to convert our moles to molecules. And the way we do this is by multiplying by Avogadro's number. So Avogadro's number is 6.022 times 10 to the power of 23, and the units are conveniently molecules over mole. So this will cancel out our moles and give us a final answer of 5.84 times 10 to the 20 molecules. Let me box it. Okay, so the junior tutor said that to solve this, we need to recall some concepts. First, that a mole is the amount of a substance that contains as many elementary entities, such as atoms, molecules, or other particles. As there are atoms in exactly 12 grams of the carbon-12 isotope, this number is called the Avogadro's number, which is 6.022 times 10 to the 23. That in mind, we just need to convert the given amount in milligrams to its amount in moles by using the molar mass of ibuprofen. Then we perform dimensional analysis. So they showed it all in one line. So starting from 200 milligrams, they converted it to grams and then divided by the molar mass of ibuprofen and then multiplied by Avogadro's number and then got 5.838835. Pretty much the same thing. So this solution is correct. Okay, so question 7. What volume of nitrogen will react completely with 29.2 liters of hydrogen to produce Nh3 at 477 Kelvin and 645 millimeters of mercury? So first, we just need to write out the reaction that takes place. We have nitrogen, say gas, plus hydrogen gas produces Nh3 gas. Okay, so now let's balance out the reaction. You'll see that we have 2 nitrogens on our reactant side, so I'm going to put a coefficient of 2 in front of Nh3. So now we have 6 hydrogens on our product side, so I just need to put a coefficient of 3 in front of my hydrogen. Okay, so the question gives us pressure and temperature. I'm going to write them down just for the sake of writing it down. Pressure and the temperature. And they give us the volume of hydrogen, which is 29.2 liters. And we are looking for the volume of nitrogen, which is question mark liters. Okay, so to answer this question, it helps if we know the formula for an ideal gas equation. So the equation for an ideal gas is PV is equal to nRT. Okay, so if you see that the temperature and the pressure are both constant for nitrogen and hydrogen, we can kind of combine them all with R since it is also a constant. So let's put let's rearrange the equation. So let's say we had volume is equal to nRT over P. Temperature and pressure is the same, and same with the gas constant. So we can kind of combine all of those variables, kind of make it equal to K. And then we can write out two formulas where the volume of H2 is equal to the number of moles of H2 times K. And then we can do the same thing for nitrogen. The volume of nitrogen is equal to the number of moles of nitrogen times K. Okay, so if we make K equal to each other, so this is reaction 1, and then this is 2. So now we have two equations and one unknown. So let's just simplify and isolate K and then make the two equations equal to each other. So to show this, these will be combined, and then we can write that the volume of H2 over NH2 is equal to the volume of N2 over the number of moles of N2. Okay, so let's make it so that our number of moles are on the same side. So we can rearrange this equation and get number of moles of H2 over number of moles of N2 and be equal to the volume of H2 over the volume of N2. Okay, so just some rearranging of the equation. And now we can kind of plug in everything that we know. We know that 3 moles of H2 is needed to react with 1 mole of N2. And we know the volume of H2 is 29.2 liters. And the volume of N2 is unknown. So if we just divided 29.2 divided by 3, this gives us the volume, which is 9.733 liters. Okay, so let's see what the junior tutor said. Write the balanced chemical equation of the problem. So N2 is equal to, N2 plus 3H2 makes 2NH3. 2, the volume of nitrogen gas is produced of the, so the volume of nitrogen gas is produced, and is measured under the same pressure and temperature conditions as the hydrogen gas. So this relationship then exists. 1 liter of nitrogen gas reacts completely with 3 liters of hydrogen gas. And then they just simplified and showed how they also got 9.733 liters. Okay, so this solution is correct. Okay, so question number 8. Calculate pH from molarity. So there are two instances on how we would do this. First, let's recall that the pH equation is equal to negative log of the concentration of protons in the solution. So in the first instance, we can have a strong acid which completely dissociate into their protons or into their ions. So if we know that strong acids completely dissociate into their ions, then this means that the concentration of our strong acid is equal to the concentration of the H+. So then we can solve for pH that way. So the second scenario is if we had a weak acid. Weak acids only partially dissociate into their ions. So in cases like this, we need to construct an ice table. Then once we have an ice table, when we solve for X, then that will be equal to the concentration of H+, and then we can solve for pH. Okay, so let's see what the junior tutor said, because they might have some examples. So this depends on what the substance is. If we have a strong acid, we simply use the relation between the pH and concentration of H+ ions. As seen in equation 1, pH is equal to negative log of the concentration of H+. Since we are given the molarity of the acid, we can know the concentration of H+ ions. Concentration of H+ is the same as the concentration of the acid, since strong acids completely ionize water into H+. We have a weak acid, so they denoted it as HA. We need to use its acid dissociation constant. This is given in equation 2. So they showed how Ka is equal to concentration of H+ times concentration of A- over HA. And note that the concentrations in equation 2 are equilibrium concentrations, which means that we need to construct an ice table for the equilibrium reaction. If we have Z, M, so like variable concentration of a weak acid solution, its ice table is shown below. So the Z would be our concentration, so like 0.1 moles per liter, or like 2 moles per liter. so depending on that. And then they show the change in X, and then this is the concentrations at equilibrium. So then we solve for X, which is the concentration of H+ ions in the solution. Knowing the concentration, we then use equation 1 to get the pH. Okay, so they also did it in the case of bases as well. So they say if we are given a strong base, we first need to get the concentration of H+ ions using the auto-ionization of water. So this is if you had a base, then you would use this relationship. So strong bases also ionize completely in water, but it ionizes to OH- ions. So by using equation 3, they can get the concentration of H+, and then solve for pH, so it's just an extra step. And you can also have an instance where we have a weak base, so it doesn't completely ionize. And they show the relationship with Kb. So similarly, concentrations of an equation 4 are equilibrium concentrations, so we need to construct another ice table and then solve for the value of X, which is given the concentration of OH- ions in solution. And then once you find the concentration of OH, you need to plug it in to the Kw equation to solve for H+. And then once you find the concentration of H+, then you plug it into equation 1. Yep, so they gave all of the different examples. So this solution is correct. So just note that every time you have either a strong acid or a strong base, it's easy to find the concentration of H+ ions, but once you have like a weak acid and a weak base, you'd pretty much just add an additional step like every time. Okay, so question number 9. Calculate the energy of a photon of electromagnetic radiation at each of the following wavelengths: 632.8 nanometers, 503 nanometers, and 0.052 nanometers. Okay, so to find the answer to this solution, we need to use the following equation, where E is equal to Hc over lambda. So E is the energy of a photon. H is Planck's constant, so it is equal to 6.626 times 10 to the negative 34 joules times seconds. C is the speed of light. So this is also a constant, 3 times 10 to the 8 meters per second. And then for lambda, this is our wavelength. So in the question, they give us wavelengths in nanometers, but we need to convert this to meters in order to use the following equation. And this is because the speed of light constant has units of meters per second. So then we pretty much just need to convert all of the given wavelengths into meters. So starting with A, we have 632.8 nanometers. And this is equal to 6.328 times 10 to the negative 7 meters. So now we just have to plug it into the equation. 6.626 times 10 to the negative 34 times the speed of light divided by the wavelength, which is 6.328 times 10 to the negative 7 meters. So the units for seconds will cancel out, and the units for meters will cancel out. And our answer is in joules, which is 3.14 times 10 to the negative 19 joules. Okay, so we can do the same thing for B. So I'm just going to quickly write in all the steps. If we converted 503 nanometers to meters, you end up getting 5.03 times 10 to the negative 7 meters. Then our units cancel out, and this gives us 3.952 times 10 to the negative 19 joules. And then lastly for C, let's write out the same thing. And then converting 0.0520 nanometers to meters, get 5.2 times 10 to the negative 11 meters. And when you multiply it all out, you should end up with 3.14 times 10 to the negative 19, or 15, sorry. Hold on, I think I wrote down. You get 3.82 times 10 to the negative 15 joules. Okay, so these are our three answers. Now we can see what the junior tutor said. To calculate for the energy of the photons, we use the equation energy is equal to Planck's constant times the speed of light divided by wavelength. Simply plug in the values to get the energy. So for A, they got 3.14 decimals times 10 to the negative 19 joules. For B, 3.9518 times 10 to the negative 19. And then lastly for C, 3.82 times 10 to the negative 15. Okay, so this solution is correct. I think we have time for one more quick question. Okay, so question 10, how are ionic compounds named? Okay, so I'll just quickly answer. It's pretty simple to name ionic compounds. First, you name the cation, which is your metal. And then you name your anion, which is the nonmetal. And then this is depending on if you have like a metal that can have multiple oxidation numbers. You can add the charge in parentheses. Yeah, so this depends on the type of metal that you have, but we can have an example. Let's say we had one copper and one chlorine. The oxidation number for chlorine is -1. So this means that the oxidation number of copper is +1. So the name of this compound is copper 1 and then chloride. So when we name our anion, we add the suffix of "ide." Okay, so let's show us another example. If we had 2 atoms of chlorine reacting with 1 atom of copper, each chlorine has a -1, but since there are 2 of them, this means that the oxidation number for copper should be +2 if we want the overall charge to be neutral. So the name of this ionic compound is copper 2 and then chloride. Okay, so the junior tutor has a very lengthy and informative response, combining the name of cation and anion. So then they just start off with binary compounds. NaCl is sodium and the chlorine ion. And then we remove the "ine" and replace it with "ide." The name of NaCl, therefore, is sodium chloride. And then for ionic compounds composed of polyatomic ions, we just combine the names of these ions. So if we had ammonium and the nitrate ion, it would just be ammonium nitrate. So it's pretty simple for that. And then another consideration we need to take is the oxidation state of some metal cations. So they show that iron can have 2 cation forms, Fe2+ and Fe3+. The name Fe2+ is also known as the ferrous ion. Fe3+ is the ferric ion. Generally, we use us for the cation with the lower number oxidation number and ik for the cation with the higher oxidation number. And then we apply the same rules for binary compounds. And then, however, the system above is helpful only for metals with 2 cation forms. And it's only used for metals with Latin names such as iron, gold, silver. So another system was developed, and this is the stock system, which designates the oxidation number of the metal by using Roman numerals. So I always found it easier to just do it the Roman numeral way, since it's still correct and you don't need to deal with the ferrous and the ferric. So this is their examples for the same compounds, iron 2 chloride and iron 3 chloride respectively. Yep, so the solution is correct. Okay, so if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. Also, don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.